Hello, student. We will see. So we have done one example. Okay, in our previous lecture, example one. So we will try to find another. We will try to do another example related with the Fourier series representation. Okay. So this is our example two. Okay. So let's say we have. We are given a signal xt is cos omega naught t. Okay, so we have to find the Fourier series representation of this signal. Okay, so this is a sinusoidal signal. Okay, so this signal is like this. Okay, sorry, signal will be like this. Okay, this is like this, no? Okay, okay. So from here to here, it is one period. Okay, so that period is 2 by omega naught t naught. Okay, is equal to t naught. Let's say it is t naught 2 by omega naught. Okay, so this is a repetitive signal. Okay, so this is a periodic signal, and we know the period also. Okay, the period is, let's say it is t naught. It is 2 by omega naught. Okay, then we are asked to find the complex. Okay, find the complex exponential Fourier series representation. Okay, so we asked to find this. Okay, so we know that this is a repetitive signal, so we should be able to represent this as a collection of complex exponential signal. Okay, so this k can be from 0, 1, 2, 3 up to plus infinity, and -1, -2, -3 up to minus infinity, so on. Okay, so if the k is 0, so you will have c0 only, because e to the power j k is 0, so you will get e to the power 0, that means 1. Okay, so this is the dc component, the zeroth harmonic. Okay, dc component. Okay, and if you, this is the first harmonic, and you will get c minus 1 e to the power j minus 1 omega naught t. Okay, and here you will have c plus e to the power j1 omega naught t. Okay, this is first harmonic. And if you, the k is equal to 2, you will have j2 omega naught t. Here you will have c minus 2 e to the power j minus 2 omega naught t. So you will get this kind of series. Okay, this kind of series, and this is zeroth harmonic, and this one first harmonic, this one and this one second harmonic, so on. So you will get up to infinity and up to minus infinity. Okay, in previous example, we see that all harmonics are not available. For that, we have found a Fourier series of this kind of signal, no? Not this kind of signal. This kind of signal, no? We have found the Fourier series of this kind of signal. Okay, and you can see that only when the k values are odd, you will get some coefficients. For k values are even, you will not have the coefficients. Okay, that means when the k are even, you will not have, you didn't get the harmonic, but when the k are odd values, 1, -1, -2, you will get some harmonics. Okay, that means there are no, all the harmonics are available, but infinite number of harmonics are there. In our previous example, sorry, yeah, infinite number of harmonics are there, but only we get odd harmonics. Okay, not even harmonic. First harmonic, third harmonic, fifth harmonic, likewise, we will have only odd harmonics, but we didn't get any even harmonics. Okay, so let's see what happened here. Okay, so now your target is to estimate these coefficients, complex Fourier series coefficients, C0, C1, C minus 1, so on. Okay, so let's get Ck is equal to minus T0. The integration should be within a period, fundamental period, that means 0 to T0 maybe. Okay, so also you can find T0 to 2T0, that is also within T0. Okay, so these things we know. Okay, so you have to choose any convenient duration. Okay, any convenient duration within the waveform. Okay, so this is 0 to T0. Let's say 0 to T0. So xt is cos omega naught t. Okay, and you have to multiply it by minus j k omega naught t and dt. Okay, to find the ck, you have to evaluate this integral. Can you evaluate this integral? I hope you can. Okay, so this integration should be done by parts. Okay, this integration should be done by parts. Okay, so you can think that this is u. Okay, and this is dv by dt. Okay, then you can perform the integration by parts, and you can find the value for this ck. Okay, ck. Okay, try to do this as a homework if you wish. Okay, but I am not going to do this. Okay, because you can see this integration, we can do this integration actually, but it is somewhat hard. Okay, and also to verify that all harmonics are there or not, okay, we have to further simplify the ck value. Okay, that one is also very hard. Okay, in our previous case, I think previous example is here. Okay, so this is our period example. Okay, so you can see that we will have only odd harmonic on including zero. Okay, we have zero harmonic, first harmonic, third harmonic, so on. Okay, but we have proved that the even harmonics are not there. No, can you remember? Yeah, here. Okay, so we have proved that the even harmonics are not there. Okay, to estimate that one. Okay, to estimate that one, we have to, okay, to estimate that one, we have to consider this sinusoidal wave and cos waveform. Okay, we have to find the value for different k. Okay, then we have to substitute the value and we have to find the coefficients value. No, okay, so it is here it is somewhat easy actually. Okay, but we have to do this for many infinite number of harmonics. No, so that is not very practical, and that is somewhat difficult. Okay, so I am trying to find another alternative method. Okay, to find the complex exponential Fourier series. Okay, okay, so I hope you get that idea. Okay, because that integration is somewhat hard. Okay, the first reason is this integration is hard. Okay, and also to find to check all harmonics are there or not, you have to substitute the k value and you have to simplify using the sine value, using the cosine value. Okay, so you have to substitute the value when you have to find that manually. Okay, so it is somewhat hard. Okay, to calculate the coefficients, calculate the corresponding coefficients, corresponding coefficient for different k value or different harmonics. Okay, uh, it is also hard. Okay, that is not easy. Okay, it is very difficult. Okay, so I am going to find the alternative method. Okay, so here we have xt cos omega naught t. Okay, I have to write this in terms of, okay, I have to write this in terms of complex exponential function, exponential function. Okay, so I have to write this in terms of complex exponential function. Actually, that is our complex exponential Fourier series representation. No? Okay, so can you imagine any method to write this as a complex exponential terms? Write this as a collection of complex exponential terms. Do you remember anything? Okay, please pause the video and try to remember. Can you remember something? Okay. Okay. So I think if you have done some example in this signal and system, okay, I think you will remember the Euler formula. Euler formula. If you remember this, okay, if you remember, when you see this, okay, when you see this statement, write this in terms of complex exponential function, okay. If the Euler formulas came to your mind, okay, you are smart, okay. So yeah, we can use the Euler formula here, no? Okay. So we have to write this in terms of complex exponential. What is Euler formula said? Okay. So Euler formula, you can see that Ej theta is equal to cos theta plus j sin theta, and E minus j theta is equal to cos theta minus j sin theta. Okay. So this is the Euler formula. Euler formulas. Okay, so you can see that if you add this, if this is 1 and if this is 2, if you add these two things, okay, so this j theta, j sin theta, you will cancel out and you will get 2 cos theta is equal to a j theta plus e minus j theta. Okay, so cos theta is equal to e j theta by half plus e minus j theta by half, no, by 2. Okay, so you will get this term. Okay, so these are complex exponential terms, no? Okay, so if I write this xt, I will have half e to the power j omega naught t plus half e to the power minus j omega naught t. Only these two terms. Okay, so what is this actually? This is the Fourier series representation. No? This is the complex exponential Fourier series representation. Fourier series representation. Correct? Okay. So you can see that. Okay. You can see that you have only one harmonics actually. One harmonics components. Okay. What is the harmonic? Okay. So what is the K value here? So it should be JK omega naught T and JK omega naught T, no? So what is the K value here? Here the K value is 1. And what is the K value here? The K value here is -1. Okay, so only you have K is +1 and K is -1. That means only you have first harmonic component. Harmonic components. You don't have a DC component here. Okay, you don't have a DC component here, and you will have you only have first harmonic components. That means you will have only one harmonic here. Okay, so here the C1 is equal to half, C -1 is equal to -half. Okay, so you have only two harmonics. Okay, so this is the coefficients, complex coefficients, and this is the complex coefficient. So you can see that although we are telling that this is a complex coefficients, these are not complex value, no, these are real value. But normally we refer this as a complex exponential Fourier series coefficients. Okay, complex Fourier series coefficients we normally refer. Okay. In previous example, I have described these things. Okay. So, did you get it? Okay. So we will try to do another one. Okay. We will try to do another example also. Okay. So let's say that we have xt equal 1 plus sine 60 plus cos 5t. Okay. So we have this kind of signal, 1 sine 60 cos 5t. Let's say this is cos 2t. Okay, cos 2t. Okay, so we are asked to find the complex exponential term, complex exponential Fourier series coefficients. Okay, so if you are going through this principal approach, okay, if you want to go this principal approach, okay, you have to find this K value. Okay, and you have to do this integration. Okay, and when you are doing this integration, the xt is more difficult, no? Okay, so here if you are going to find the coefficients with that principal approach, okay, the xt you will get 1 sine 60 plus cos 2t e to the power jk omega naught t dt minus jk omega naught t dt. Okay, so this is the xt. No, so this integration is very difficult. No, so you have to do very long integration. Okay. So you no need to go through this method. Okay, so what you can use here, you can use the Euler formula. Okay, you can use the Euler formula, but before that we have to verify that this is periodic or not. So we have to do that, and also we have to find the period also. Okay, so we will see. Okay, so now you have to go back to your LO1 content. Okay, find the composite signal is periodic or not. What is the procedure? Okay, so you have to, so we this kind of things we have done in our LO1 content. Okay, find the period of a composite signal. Okay, so this is a composite signal. Okay, it has some different sinusoidal value, and also it has a DC value, DC component. Okay, so so you have to find the period of this signal. So what is the procedure? First you have to consider this terms as separate three signal. Okay, and if you consider x1t, that is 1. Okay, So you can consider this as this is a periodic signal, and period can be anything. Okay, period can be anything. Period can be any value. We have explained this thing. Okay, we have already done these things. Okay, x1t is equal to 1. Period can be any value. Okay, and if you consider x2t, that is sine 60. So you know the period here. This is a periodic signal, and you know the period. Period is, this is omega naught. Okay, so let's say the period is t2 here. Okay, so that is 2 pi by 6, 2 pi by omega naught, 2 pi by 6. Okay, I'm not going to explain this further. Okay, you have to refer the previous content. Okay, so this is the fundamental period is 2 pi by 6. Okay, and if you consider the x3 signal, x3t signal, that is cos 2t. Okay, and you, if the period is t2, that is 2 pi by 2, 2 pi by omega naught, 2 pi by 2. Okay, so this is the period of t2 and t3. To find the common period, you have to get the ratio. No? Can you remember? You are going to get the ratio. So what is that ratio? T2 is 2 pi by 6. And you should divide it to 2 pi by 2. No? So here 2 pi by 2 to come to above. Okay, so this is like that. So 2 pi cancelled out, and you will get 1 by 3. Okay, so if this is a rational number, these two signals are periodic, so this is a rational number. Rational number. So this is periodic. To find the common period, you have to find the least common multiplier. No? Can you remember? Okay. To find that, you can see that this is 3t2 equal to t3. Okay, and this is the composite signal period. 3t2 or t3. Okay, so what is t3? This 2 cancel out, and you will get 5. Okay, so this 5 is the composite signal period. Okay, so I hope you can understand this. Okay, because we have done these things. Okay, so t is 5. Okay, so for this signal and this signal, t is 5. Okay, t naught is 5. Okay, the fundamental period, let's say it is t naught. T naught is 5. Okay, and for this term, dc component, period can be any value. So let's assume that period also 5. Okay, so this periodic, this is a periodic signal, and the period is 5. Okay, so we are given xt 1 sine 6t plus cos 2t. No, sine 6t plus cos 2t. Okay, so this is periodic signal. Periodic signal. Okay, and the t naught is 5. The period is 5, and omega naught is 2 by t naught. Okay, that means omega naught is 2 by t naught. T naught is 5. That means t5 by 5. So omega naught is 2. Okay, so omega naught is 2. This value also somewhat important. Okay, now we see this information. Let's see how can we write this as a collection of complex exponential function. Okay, so you can use the Euler formula. Okay, so sine 60, you can write it as half e to the power j 6t minus half e to the power j, sorry, I find that one, I can't remember. Okay, so you know that e j theta is equal to cos t. Okay, e j theta e j theta is equal to cos theta plus j sin theta, e minus j theta equal to cos theta minus j sin theta. This is 1, this is 2. Okay, so you have to find the sin theta. Okay, then you have to, if you subtract 2 by 1, okay, so you will get this cos theta cancelled out, and you have j sin theta minus j sin theta. That means 2j sin theta is equal to e j theta minus e to the power minus j theta. Okay, so sin theta, you will get half 2j e to the power j theta minus half 2j e to the power minus j theta. Okay. So if you write this xt, okay, if you write this xt, okay, if you write this xt, then is there, okay, and sin theta you can write it as 1 by 2j e j, now theta is 60, g 60 minus 1 by 2j e j minus ej 60. Okay, plus this cos 2 theta you can write it as, previously we also see it as half e to the power j 2t plus half e to the power j 2t. Okay, so we can write this like this. Okay, so now how to find the, so this is the Fourier series representation. So this is the Fourier series representation. Okay, now we have to find, so you can see that also here also we have limited harmonics. No, for this also we have limited harmonics. Okay, we have limited harmonics. Okay, so so let's see what are the harmonics are available. Okay, so you can see that this is the DC component. No, so that is zeroth harmonic. So here DC component is there. Okay, that means zeroth harmonics are there. That is one. Okay, what about other harmonics? You have to estimate them. Okay, you have to see what harmonics are there. The first harmonic, second harmonic, third harmonic. Okay, but here you can't see it correctly, directly. Okay, so you can see that in our previous example we have told that, okay, we have told that, okay, so you see, so the, so we have zeroth harmonic, okay, and we have first harmonic, that is omega naught, the frequency is omega naught, and the second harmonic, the frequency is 2 omega naught, the third harmonic, frequency is 3 omega naught. Okay, so all harmonics are written with respect to omega naught, no, omega naught. Okay, and the 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 multiplier value of the omega naught is the harmonic value, no, harmonic number. Okay, so this one also we will write in terms of the omega naught. Okay, so what is the omega naught here? The omega naught is 2.5. Sorry, omega naught is 2. Okay, omega naught is 2. Okay, omega naught is 2. So I can write this xt again as 1, okay, 2j e to the power j 2 omega naught is 2, okay. So I write as 3 by 2. This is omega naught minus half 2j e to the power minus j. So omega naught is 2. So here there are 6, no? So we have 3, 2, 3, 2. This is omega naught t. And here this is half e to the power j 2 is there. Okay. So you have 1, 2, t. So this is omega naught. Okay. And here you have half e. This is minus. Okay. Minus j. Okay. That means minus 1, minus 1 to t. Okay. Okay. So if I write this in terms of omega naught again, I will have this kind of 1. No? Okay. So I will write this 1 here. Okay. 1 here. Okay. And I will write this term. Okay. So this is, if I write this term, no, I will write, I think they will get confused. Okay. So I can write this as 1. Okay. 2j e to the power j, here 3, this 2 is omega naught, no? 3 omega naught t minus 2j e to the power, so here j minus 3 omega naught t, correct? Omega naught is 2, okay? Half e to the power j 1 omega naught t plus half e to the power j minus 1 omega naught t. Okay. So these are the k value, no? These 3 are this minus 3, this 1, this 1 are the k value, no? K omega naught t, k omega naught t, no? Okay. So you can see that this k, this k is 3, and here also k is minus 3. So these are third component, third harmonics. Okay. And here the k is 1, and here the k is minus 1. So these are first harmonic. And here the k is 0. That means DC component. So I can write this as like this: 1 plus half e to the power j 1 omega naught t plus 1 by 2j e to the power j 3 omega naught t so on. So only one that term. Okay. Here I can write this term half e to the power j minus 1 omega naught t plus here this term minus 1 by 2j e to the power j minus 3 omega naught t. Okay, so this is the DC component, and this one are first harmonic, this one are third harmonic. No, this is third harmonic, and this is first harmonics, and this is the zeroth harmonic. So the coefficients I have C0 I have, that is 1. Okay, C1 I have, that is this one, no? Half. Okay, and C minus 1, that is this one, again it is half. Okay, and C2 not available, C3 is there, this one, and this is the component, the coefficients, that is 2j. Okay, and C minus 3 also there, that is minus half 2j. Okay, so these are the coefficients. Okay, so I hope you get it. Okay, so we will stop now. Okay, so as a homework, try to evaluate the coefficients of this signal. 5t plus 4 sine 35t plus 5 by 2. Okay, so try to find the Fourier series representation of this signal. Okay, find Fourier complex exponential Fourier series representation of yt, this signal. Okay, so as homework you can do this. Okay, so if you have any problem you can ask. Okay, okay, thank you.